Let me ask them to join for the last time. So that is the meaning of calorimetry. Measurement deals with the measurement of heat. Measurement of heat using network. Hello. Hello.
Hi.
I had network instability. I think it's back now. So I hope you can hear me. Can you hear me? Class, can you hear me?
Yes, please.
Okay. So it's a measurement of heat using the calorimeter. So the principle is calorimetry. The instrument used in doing this is known as a calorimeter. Okay. So calorimetry deals with the measurement of heat using the calorimeter. Now, the principle behind calorimetry is that the principle of operation of, or the principle, let me coin it as the principle of calorimetry. The principle of calorimetry is that when two bodies are said to be in thermal contact, and they dwell in the two bodies and they exist or dwell in isolated states. Heat energy can be transferred from heat energy is transferred from the body at a higher temperature to the body at a lower temperature until thermal equilibrium is obtained or is attained. So We discussed this principle in our last meeting. Now, when two bodies exist in an isolated system, heat energy can be transferred from the body at a higher temperature to the body at a lower temperature, and it will only stop when the two bodies have attained the same temperature. This is what we term as thermal equilibrium. Okay, so that's the principle behind calorimetry. That when two bodies are in thermal contact, and when two bodies are in thermal contact, it means that the two bodies can exchange heat energy. Okay, so when they exist, when they are in thermal contact and are in isolated state, heat energy can be transferred from the body at a higher temperature to the body at a lower temperature, and will until thermal equilibrium is attained. That is the principle of calorimetry, the principle behind calorimetry. Please, are you okay? Are you hearing me out? Because the network seems to be disturbing.
Yes, please.
Okay, so that's the principle behind calorimetry. And last time we went through this and then came to the realization that when two bodies exist in thermal contact and they find themselves in an isolated state. So I gave this diagram where we have two bodies. This is an isolated system. We have body A and then body B. If the temperature of A is greater than the temperature of B, we'll have heat energy being transferred in this direction. Okay, so body A loses, whereas the body at a lower temperature gains. And it will only stop when the transfer will stop when the temperature of A is equal to the temperature of B. And this is the principle behind calorimetry, heat measurement. That's the principle behind calorimetry. Now we can use the principle of calorimetry to determine the specific heat capacity of substances. So the principle of calorimetry can be used to determine the specific heat capacity of substances. The substances here can be liquids or solids. As for gases, because gases cannot be seen, we can use, so example, liquids or solids. So we can use the principle of calorimetry to determine specific heat capacity of substances. Class, what did I say? What did I say about the usage of the principle of calorimetry? Yes, can somebody tell us? What is the usage of the principle of calorimetry? Let me call one of you two. Julian.
W is used to determine the specific heat capacity of a substance.
Okay, so can somebody tell me what specific heat capacity is? what do we mean by the specific heat capacity of substances? Mamiya.
It is the amount of heat energy required to change the temperature of a body.
Mamiya, I'll give you 3.5 out of 5. You are missing something. Prince.
Heat capacity is the amount of heat that must be absorbed or liberated in order to change the temperature of a material by 1 degree Celsius or Kelvin.
4 out of 5. 4.5 out of 5. I said, what is specific heat capacity? Mamiya again.
It is the amount of heat energy required to change a mass of 1 kilogram of a substance by 1 Kelvin or degree Celsius.
Thank you. You have the full marks now. So, Prince, what you said was also true, but you were talking about heat capacity. You know, with heat capacity, we are not looking at specific mass. Okay. So, with specific heat capacity, we are looking at 1 kilogram, 1 gram, or what we call as a unit mass of a substance. And please, the change is about raising the temperature by 1 K or dropping it. So it is the amount of heat energy that must be absorbed or liberated, give away, in order to change a unit mass of a substance or a material by 1 Kelvin or 1 degree Celsius. All right, so we can use this principle of calorimetry to determine the specific heat capacity of substances or materials. How do we do it? We have 2 methods of doing this. We have one using the method of mixture. By the method of mixture or electrical method. So we'll go through the 2 procedures using the method of mixture. Method of mixture. 1, by using the method of mixture, method of mixture, and then 2, using the electrical method. What is the method of mixture? In the method of mixture, I earlier said that the instruments or the gadgets used for doing this is a calorimeter. The calorimeter is a vessel like similar to the vacuum flask. This is like a copper vessel. It's a copper vessel. Then it has a lid. It has a lid. Am I drawing? So it has a lid. It's something like this. Then there is an outlet of the lid where a thermometer is inserted, can be inserted. So this is a hole where thermometer is inserted. So let's take this to be a thermometer. Okay. Then within the same lid, we have a stirrer. So this is also a stirrer. Now the calorimeter itself is a small vessel. It's a small vessel. So this is the inner small vessel, which we are calling as a calorimeter. Around the small vessel, we have what we call a lagging effect. You see, in a vacuum flask, there is space between the flask, the vacuum flask itself, and its plastic container outside. Within this, we have lagging materials such as styrofoam. In the case of the calorimeter, it can be styrofoam, it can be sawdust, solid, yes. The reason is that we wouldn't want the calorimeter, which is this inner container, to establish contacts with the copper vessel. This is a calorimeter itself. This outside one is the copper vessel. And then this is the lagging material. The lagging material, which can be a styrofoam, which can be styrofoam or sawdust or fiber. It can even be coconut fiber. The idea is that we must put something in between the calorimeter and then the copper vessel, and the thing must be a non-conducting material, anything which will not take heat energy from the calorimeter to the surrounding. Okay, we have the same thing also here, lagging material also here, so that we minimize heat loss as quickly as possible, because this thing must exist in an isolated state. So if it is an unknown liquid, okay, if whatever the substance or the material whose specific heat capacity is to be determined is a liquid, then we have a liquid of mass m. Its specific heat capacity, that's what we are looking for. So specific heat capacity unknown, that is Cx, unknown, X to represent unknown. Then what we do is that we determine the initial temperature. The thermometer inserted within has a function of determining temperature. So let the initial temperature be T1. Then we must also know the mass of the calorimeter itself. So let the mass of calorimeter be MC. MC. Of course, the liquid and then the calorimeter would have the same initial temperature. When you pour ice water in a cup, the temperature of the ice the water within and the temperature of the cup will be the same. So initially, temperature of the calorimeter itself, temperature of the substance in there is the same, T1. Okay. Now what we do is that we heat a substance, a metal. We heat a substance, which is a metal, to maybe the temperature of 100 degrees Celsius. So this is a metal that is heated. So this serves as the source of heat. We heat this to a temperature of maybe 100 degrees Celsius. Then when this substance, the mass of this substance, MS, okay, is heated, and then we connect a thread to this so that we can easily remove it from the water. So this is a thread connected to it. The essence of it is to enable us to just take it from the source of fire when it is being heated to this temperature. So when it is heated to this temperature, we quickly transfer the hot substance to the calorimeter. So quickly we transfer. So we have the metal placed in the calorimeter. And then now once we transfer, the idea behind what we are doing is that this is a hot body. Okay, it will lose heat. Energy is always transferred from a body at a higher temperature to a body at a lower temperature. So because the temperature 100 is greater than the initial temperature of the water, the liquid, and then the calorimeter, which is T1, we'll have heat energy being transferred from the metal to the liquid and then to the calorimeter. Please, class, are you following? Are we following?
Yes, please.
Okay. So there will be transfer of energy, and provided we do this in an isolated state, heat energy will be transferred from the body at a higher temperature to the body at a lower temperature, and we'll cease when the two bodies have attained the same temperature. Let's assume that at thermal equilibrium, the temperature of the mixture is T2. So let's temperature at thermal equilibrium be T2. So be T2. Okay. So the temperature where the transfer of heat energy will cease is T2. Now, when you put hot water in a cup, you realize that not even hot water, if we have cold water in a cup, and then you heat a metal and transfer it into the cup containing the cold water, you realize that the cold water will gain heat energy, so will become hot. So would be the cup itself. The cup would also gain heat energy from the metal which was transferred. So in transferring the metal itself will lose heat energy, but heat energy will be gained by the water within the cup plus the cup itself. Please, are you okay? So it isn't only the water which will gain energy, heat energy, and heat energy will be gained by the water plus the cup which contains the water. Julian, are you okay? Angel, are you okay? Or Henry? Friends. Okay. So when we transfer, and then you see the function of the stirrer, we will stir the mixture. By stirring the mixture, you want even distribution of the heat energy within the container. So you push the stirrer up and down to have a uniform distribution of heat energy from the hot body. Okay, you do that. Okay, and we'll stop when you realize that there's no change in the thermometer reading. So if there is no change in the thermometer reading, then it means that the hot body, the cold body have attained the same temperature. So we are at thermal equilibrium. Please, is there any question? Is there any question? If you have any. So this, before we,
Mr. Adia, please, I wanted to ask that the initial temperature, is it the temperature of the calorimeter or the temperature of the liquid?
However, if you pour water in a cup, the temperature of the cup, the temperature of the liquid is 1. Okay. Once the water is poured into the cup, they will both have the same temperature. So T1, the T1, which is the initial temperature, refers to the temperature of the water and then the calorimeter itself. Julian.
Sir, please, the cup, is it plastic or it's metal?
No, it's a copper vessel. The calorimeter is a copper vessel. And then
Like I mean, in your illustration, your example you were giving.
Oh, it can be, in my example, it can be a plastic or a glass. You see, when you pour, if you have cold water in a cup, and then you pour hot water into it, the cold water within the cup gains heat energy from the hot water. So would be the cup itself. When you are preparing tea, and I mean, and then you fill in, okay, you have cold water and then you pour it. That's what happens. Both the cold water and then the container gains heat energy from the hot water. Are you okay?
Yes, sir.
So that is applicable to whether it's a glass or plastic. Elizabeth.
Sadia, please. You were talking about a stirrer. Is a stirrer inside?
Yes, it's
or that
the stirrer is inside the calorimeter containing the liquid specific heat capacity is calculated.
So that's not a thermometer.
Oh, we have a thermometer and a stirrer in there. So this is the stirrer. This is the stirrer. And then we also have this. Okay. We are not here to draw, so my drawing is not so clear. Thermometer. So within the calorimeter itself, we have the stirrer, we have the thermometer. The function of the stirrer is to ensure evenly distribution of heat energy within, and then the function of the thermometer is to record temperature change till thermal equilibrium is reached.
Yes, please. Thank you.
All right. Okay, now this is the method of mixture. Let's go into the equation. So we are saying that once the metal is transferred, heat energy loss by what? What will lose the energy? What loses
the metal?
By the metal. By the hot metal. must be equal to heat gained by what? Energy gained by what? Energy gained by, yes, let me hear from you. Plus energy gain, heat energy gain by the
liquid.
The liquid.
By the liquid. Is it only by the liquid?
And the
The liquid and the
calorimeter.
calorimeter.
The container, yes, calorimeter. So by liquid and the calorimeter. So we
So
have,
is this before the thermometer and the stirring rod is put inside, or
oh, the thermometer and the stirring rod are within. We are, in fact, the assumption is that the thermometer must actually conduct energy to record a change in temperature. So small amounts of heat energy actually will be taken by both. Okay, but we are also creating a situation where the heat energy gain will not escape. The reason why we have the lagging effect, but we actually overlook what is gained by the thermometer and of the stirrer. We don't take account of it because they are very, very small. Julian, are you okay?
yes, sir?
So mathematically, we said Q loss must be equal to Q gained by liquid plus Q gained by calorimeter. And from the principle of conservation of energy, the total energy lost by the metal must be equal to the total energy gain. Okay, if this dwells within isolated system. So this is an equation establishing the conservation of energy. All right, so how do we determine the K.O. loss? Can somebody help? How do we determine the heat energy loss? Anybody to help? Priscilla, you are there, so talk. So please, it can be answered by any one of you. How do we determine the heat energy loss by the metal? Can somebody help me? Okay, Refwa.
Mr. Dear, please, it will be the mass of the metal times the specific heat capacity of the metal, then times the temperature of the metal before it was put in the liquid, minus the temperature of the metal after thermal equilibrium.
Okay, so thank you so much, Refwa. So let the mass of the metal, you can say mm times the specific heat capacity of the metal must be known. So Cm, then the change in temperature. The change in temperature is that the initial temperature of the metal, which is 100, will certainly be greater than the temperature after thermal equilibrium. So T of the metal minus temperature at final thermal equilibrium is T2 minus T2. Don't forget here, we took this to be 100. So depending on how you want to heat the substance. Okay, so this will be the heat energy loss. What about the heat energy gained by the liquid? Can somebody help? Q gain by liquid. Can somebody help? The heat energy gained by the liquid. Anybody? Okay, a river again.
Mr. Dia, please. Mass of the liquid. No, first of all, it will be the mass of the calorimeter minus the mass of the liquid.
Okay, so
Or
a river.
okay.
Here, the mass of the liquid must be known. Don't forget, we can even calculate, okay, how to determine mass of liquid. Weigh an empty beaker, record the mass, pour the liquid, reweigh, subtract the mass of the empty beaker from the mass of the beaker plus the liquid. So we can always determine the mass of the liquid. Go ahead.
Okay, so it will be the mass of the liquid times the specific heat capacity of the liquid times T2, that is temperature after thermal equilibrium, minus the initial temperature,
Which we indicated as T1.
which is T1.
Yeah. Please, are you all following?
Yes, sir.
I just want to take attendance. All right. So, Arefa, thank you. All right. So, this will be mass of the liquid ml Cx. X because we don't know. So, let me also use L in order to match the letters I'm using. Then the change in temperature will...
Mr. Dia,
Hello.
please, you indicated the mass of the liquid as mx.
Yes, from here, but I'm changing it to L so that it will indicate liquid. Okay. So make the changes. So change in temperature, the final temperature at thermal equilibrium will certainly be greater than the initial temperature of the liquid and the calorimeter. This is because when the metal is dropped, the liquid and calorimeter will gain heat energy. So it will increase their internal energy. So T2 will certainly be greater than T1. So when we are looking for the change in temperature, it is T2 minus T1. Then heat energy gained by the calorimeter. Somebody to also help. Somebody to help me get the equation for heat energy gained by the calorimeter. Prince, come in. Nana Safu, you're also there. Priscilla, you are there too. Oh, okay. Priscilla, go ahead.
Okay, so the mass of the calorimeter
Okay.
times the specific heat capacity of the
So CC.
times the final temperature minus the initial temperature.
Oh, thank you. So initially, temperature of the calorimeter and the liquid the same. So if we are looking for the change in temperature, that's it. Still T2 minus T1. So let's put all the three equations together. Can I clean the calorimeter? Yes. Even when you...
Yes, please.
It's gone already. Mommy, are you there? So
yes, please, I'm here.
If we connect the two, we have mass of metal, specific heat capacity of metal, T of metal minus temperature at thermal equilibrium equal to mass of liquid, specific heat capacity of liquid, T2 minus T1 plus mass of cal, C of cal, and still T2 minus T1. Now, our point of interest is on the specific heat capacity of the liquid which we are looking for. So since whatever we are looking for is here, we send this to the other side of the equation. So ML CL T2 minus T1 would be equal to CM TM minus T2 minus CC T2 minus T1. So that because we are looking for this, we divide through by ML T2 minus T1 ML T2 minus T1. So this and this will cancel out so that our unknown, which is CL, will be equal to CM TM minus T2 minus CC T2 minus T1 all over ML. This is how we can use the principle of calorimetry to determine the specific heat capacity of an unknown liquid. If it's about the specific heat capacity of the metal, it's the same thing. All that we do is to make CM the subject. If it's of the calorimeter, the same thing. So this is how to use the method of mixture to determine the specific heat capacity of an unknown liquid. And if you could identify the specific heat capacity of the liquid, you can also identify the liquid. Because if in a calculation I get the specific capacity of a substance to be 4,200 joule per kilogram per Kelvin, what is this substance? Or what substance is this? Yeah, Julian.
Is it ice?
Julian, is not ice. If in an experiment, there's a reservoir. Water. So knowing specific heat capacity, you can easily identify substances. Okay. All right, let's solve a question. How to apply this in solving problems. Are you ready? I'm reading out the question. Are you ready? A 6.0 kilogram piece of iron. A 6.0 kilogram piece of iron at 100 degrees Celsius is immersed in 3.0 kilogram of water. Is immersed in 3.0 kilogram of water at 20 degrees Celsius. I take it again. A 6.0 kilogram piece of iron at 100 degrees Celsius is immersed in 3.0 kilogram of water at 20 degrees Celsius. Determine the final temperature when thermal equilibrium is attained. Determine the final temperature when thermal equilibrium is attained. Take the specific heat capacity of water to be 4,200 joules per kilogram per Kelvin, and take the specific heat capacity of iron to be 2,700 joule per kilogram per Kelvin. Take the specific heat capacity of water to be 4,200. Oh, sorry. The specific capacity of iron is 450 rather. The specific heat capacity of iron is 450 joule per kilogram per Kelvin. Make me proud.
Sir, could you please take it again?
Okay, so listen for the last time. A 6.0 kilogram piece of iron at 100 degrees Celsius, a 6.0 kilogram piece of iron at 100 degrees Celsius is immersed in 3.0 kilogram of water at 20 degrees Celsius. Is immersed in 3.0 kilogram of water at 20 degrees Celsius. Determine the final temperature when thermal equilibrium is attained. Determine the final temperature when thermal equilibrium is attained. Take the specific heat capacity of water to be 4,200 joules per kilogram per Kelvin, and the specific heat capacity of iron 450 joule per kilogram per Kelvin. I'm coming in. I'm coming. Your hand was up. Mamiya.
Please, I had 34.1 degrees Celsius.
34.1 degrees Celsius. Who else? Who else managed
They
to?
said that same answer.
Okay, so let's see.
You could have the same answer.
Okay. The gentleman, Julian, Prince, and Co. So, Q lost by ion must be equal to Q gain by water. Here, there's no other substance. It's just heat lost by ion, heat gain by water. And we have M of ion, M of ion, C of ion times change in temperature. So the change in temperature would be 100 minus T final, which we don't know. This is also equal to mass of water, C of water. T final will be greater than the initial temperature of water. So minus 20. So let's substitute our figures. 6 times 450 times 100 minus TF is equal to 3 times 4200 TF minus 20. Okay. So what is left is multiplication, but this 3 can go into this 2. This 2 here can also go into 420, 210. Okay, so that we have 4500 minus TF is equal to 210 TF minus 20. Maybe you don't want to drop the value of the number again. So 4500 minus 45 TF is equal to 210 TF minus 4200. Are we okay? Hello, are we fine?
Yes, please.
Then we group like terms. 4500 plus 4200 is equal to 210 plus 45 TF. Let's add this. We have 8700 is equal to 255 TF. When we divide through by 255, what's the answer? What's the answer?
34.118.
So the temperature at final equilibrium 34.12 degrees Celsius. That is the final temperature. So those of you who called out 34, you got it right. Please, is there any question to ask in the solution? This is how to determine the final temperature. Now, another use of this is that We can also use this method of mixture to determine the temperature of a very hot, very warm source of fire, such as furnace or oven. The source of fire which can't be accessed easily. Maybe because of its intensity, you can't easily go close to take measurements. Okay, so we can also use this method to determine the temperature of a very warm source. Example, furnace, a furnace. How do we do it? Because the source is so warm, or the temperature is very high, you can find a way to drop, if it's an oven, put the substance in this receptacle with a very long handle, okay, so that you place it within the furnace, and the handle must be long enough so that if you want to take it, you can easily drag it, okay, from the furnace. So you allow the metal to be heated for some time, okay. You want to record the temperature of the source, but because the temperature is so much that, or the source of heat is so much that you can't go near, you put a metal, use a very long receptacle and push it into the oven or the furnace. Let it be heated for some time. Then you quickly transfer into the calorimeter containing water. Okay, so it has the thermometer, it has the stirrer. So by then you should record mass of water, the mass of this metal. Okay, you must know the specific heat capacity of water, specific heat capacity of the metal, and then you must also know the initial temperature of this. So T1. Now, when the metal gets into it, you stir. You stir to have evenly distribution of the heat energy, and then you only stop when thermal equilibrium is reached. Now, when thermal equilibrium is reached, Q loss by the metal must be equal to Q gained by water plus Q gained by the calorimeter. If here we want to include the details of the calorimeter. Okay. Now Q loss by this is equal to mass of metal, specific heat capacity of metal, then Tx. Tx is the unknown temperature of this source, the furnace. So Tx minus temperature at thermal equilibrium, maybe T final, is equal to heat gained by the water, blah, blah, blah. Okay, so Q gained by water plus Q gained by calorimeter. Since this is the part of we are interested in, we divide through by this. MM CM. Then finally, Tx will be equal to KW plus QC, all divided by CM, okay, plus T final. So this expression here would give you the estimated temperature of the furnace or the source of fire. Please, is that okay? Are we okay?
Yes, please.
All right. Now, this value, estimated temperature, would actually be less than the original amount as it's supposed to. It will not be the actual amount. It will be a little bit less than. Why? Why do you think Tx, the estimated temperature of the source, wouldn't be the actual, but it will be a little less than the actual value? Why? Can somebody brainstorm and share with us why he or she thinks that would be the issue? Can somebody think through and share with us? Julian, you are there. Safo.
Yes, sir.
Julian, can you think?
Sir, please.
Hmm.
Can I say that since the source of the fire is not coming from an isolated system sometimes?
But when it was also heated, when the metal was heated and dropped, the metal, the heating vessel and the metal was not within. It was outside, but was heated for some time and we transferred. So still, the isolated situation must be between the metal that is dropped, the water, and then the calorimeter, rather not the external source. Are you okay?
Yes, sir.
More views. Why? Why? A. Oh, Elizabeth, Eurefua. Let me look at faces. Eurefua,
Mr. Edia, please, because the after the metal has been removed from the furnace, a lot of like factors will actually before it to be dropped in the water. So it will not be the actual value. And also after the
factors such as is it
like
I'm listening. Are you stuck?
okay, so factors like maybe air can also reduce.
So what is a
Yeah,
what are you saying? What are you saying
that
as to why it will not be the actual value?
because after the metal has been removed from the furnace, external factors such as air will act on the metal before it is put into the calorimeter.
So what is a river actually saying? You are close, but you are not hitting the nail on the head. That is why I'm probing. Okay, all right, because of time's sake. It's true. But you see, what you really wanted to say is that when it is removed, because it has to be moved and dropped into the calorimeter, heat energy will be lost to the environment before it is dropped. Please, is that okay?
Yes,
Yes.
It is somewhere. So I have to take and then move. So during the course of movement, heat energy will be lost to the environment. So what I will eventually record will be a little less than the actual source because of the drop or the the drop in the amount of energy. So during it will happen, there will be drop due to the transfer of the hot substance into the closed isolated system. Please, is there any question? If no question, let's move on to the electrical method. How do we also use the electrical method to determine the specific heat capacity of substances? So we've gone through the method of mixture. So calorimetry, this is it. Not so difficult, but you just need to understand the principle. And then now we are still using the calorimeter. So the copper vessel, within the copper vessel, we have the calorimeter itself. Then this time around, we insert an immersion heater. So this is an immersion heater. We also have a thermometer. Record initial, record the final. This time around, we will not stir. Now, the immersion heater must be connected to an ammeter. So this is an ammeter to record current. This is a source of EMF. We have a source of EMF. Let me use AC. So it's an AC source. So then we connect a resistor. Let me bring the resistor here. R. This is a resistor. Then a source of AC. Then across this resistor, we connect a voltmeter. V. So if this is the circuit of the immersion heater, R, this is EMF, source of EMF, and then the voltmeter connected across the resistor. This is an ammeter. In some other circuits, we also have a key. So that will be controlling the flow of current. The key behaves as the switch in your room. This is still the LED. The LED of this. This is even not so necessary. Now the ammeter would record the current flow. V will record the voltage drop across the resistor. EMF is the driving force of current. We still have the thermometer, which will measure initial temperature and then final temperature. Now, so this is a circuit, the electrical method circuit. Here, you see, the heating is being done by, before we heat an object okay, somewhere using source of fire and then transfer. This time around, the heater is going to do the heating for us. So the heat energy that will be gained by the liquid within the calorimeter will be done by electrical means. Okay, so in deriving the equation or establishing the equation, heat loss by immersion heater. Heat loss by immersion heater must be equal to heat gain by liquid plus heat gain by calorimeter. That will be the equation. Okay. Now, since the heat energy, are you listening? Are you there?
Yes, please.
In this method, since the heat energy is provided by the immersion heater, okay, there is energy conversion. Electrical energy will be converted to heat energy. Electrical energy within the coils will be changed to or converted to heat energy. So the heat energy provided, the heat energy supplied is equal to the electrical energy, okay, flowing through the meter or supply is equal to the electrical energy. So all that I'm saying is that the heat energy loss is provided by electrical energy due to energy conversion. So if you want to calculate the heat energy loss by the heater, we must calculate the electrical energy. Okay. So how do we determine electrical energy? Electrical energy is equal to the power rating of the heater. The power rating or requirement of the heater times the time taken for the use of the heater. So if you use the heater for 30 minutes, the electrical energy consumed will be the power rating of the heater. Most heaters have rating 20 watts, 120, 100 watts. So if your heater's power rating is 120 and you use it for 30 minutes, the electrical energy consumed will be 120 watts times 30 minutes. 30 minutes in seconds is equal to, what is 30 minutes in seconds? 30 minutes in seconds. 30 times.
So 1,800.
So 1,800 seconds. So when you multiply this and this, that will be the electrical energy. So the heat energy lost or supplied by the heater would be equal to this, since electrical energy will be converted to heat energy. So in the electrical method, we equate the electrical energy, which is power times the time, to be equal to the heat gained by the liquid, KOL, plus heat gained by the calorimeter. So PT would be equal to ML CL times change in temperature. The final temperature reading minus the initial, so T2 minus T1. Here I'm assuming that the initial temperature of the system, water, and then the calorimeter is T1. And after it has been heated for that time period, the final temperature is T2. So plus the same thing, MC CC times T2 minus T1. So this is the electrical method. One form of equation that can help us calculate whatever. So if the emphasis is on determining the specific heat capacity of liquid, you make this the subject. If it's about the calorimeter, that's it. Please, any questions before I continue? Any question? Julia,
No.
Elizabeth, Erefa. Kezia,
No, please.
Another possible equation is that from Ohm's law, power, electrical power. Let me take you through some Power, electrical power is equal to, or energy in itself is equal to power over, no, I'm coming. Energy is PT. Okay, so energy is equal to PT. The reason for which we equated this to this, meaning power is equal to energy over time, or work done over time. Okay, work done over time. Now, in electrical, work done in current electricity, W is equal to charge times voltage. Work done in current electricity is given as this, QV. Meaning that from this equation, power will be equal to, if we substitute whatever we have for W here, we have QV over T. In the same current electricity, current I is equal to charge over time. So current is equal to the rate at which charges move within a given time. So it means that this Q over T is current from this equation as well. So power will therefore be equal to IV. Okay. All that I'm saying is that in place of power, we can also put current times voltage. Electrical power is also given by current, the product of the current and the voltage. And that's the reason why in our circuit, we have the ammeter to read the current flow, the voltmeter to read the voltage across the resistor. And so this same equation can also change to another form. You haven't done current electricity, so you will not enjoy this so much. But once we are doing calorimetry, I need to talk about it. So we can substitute IV for power, and it will be current times voltage times time being equal to the right-hand side. Q of L plus Q of C. In fact, there are lots of equations which we can derive, but because you haven't done current electricity, I am not comfortable disturbing you with those rigorous equations. Do we discuss it or leave it here? And here.
The end.
Because once you haven't done the topic, when I apply, you wouldn't enjoy so much. Okay. So this is the electrical method. The electrical method. Okay, let's try a question on calorimetry, the method of mixture. A question. A 0.05 kilogram metal, a 0.05 kilogram metal is heated to 200 degrees Celsius. Is heated to 200 degrees Celsius and then dropped.
Please, can you take it again?
All right. Prince noted. Okay. Once I'm recording, you'll be catered for. So a 0.05 kilogram metal is heated to 200 degrees Celsius. Is heated to 200 degrees Celsius. And then dropped into a beaker. And then dropped into a beaker containing a 0.4 kilogram of water. And then dropped into a beaker containing 0.4 kilogram of water, initially at 20 degrees Celsius. Initially at 20 degrees Celsius. If the final equilibrium temperature of the mixture, if the final equilibrium temperature of the mixture is 22.4 degrees Celsius, if the final equilibrium temperature of the mixture is 22.4 degrees Celsius, find the specific heat capacity of the metal. Find the specific heat capacity of the metal. That is A. And B. And B. And B. What is the energy transferred to the water as the metal is cooled? What is the energy transferred to the metal, to the water as the metal is cooled? I'm coming. I want to give you the specific heat capacity of. Oh, okay, that is what is being asked for. So find the specific heat capacity of the metal. You know the specific heat capacity of water. So make me proud. So a 0.05 kilogram metal is heated to 200 degrees Celsius and then dropped into a beaker containing 0.4 kilogram of water, initially at 20 degrees Celsius. If the final equilibrium temperature of the mixture is 22.4 degrees Celsius, find the specific heat capacity of the metal. And B, what is the energy transferred to the water as the metal is cooled? Make me proud. 6 minutes. The problem of the afternoon. Aheneba. Aheneba. Oh, he's not here. Look, heat gained by the beaker. So if in a question that is given to you, fine, you take care of it. Okay. So if the temperature at final thermal equilibrium is 22.4, find the specific heat capacity of the metal. So fuel loss by who? Metal is equal to fuel gain by water. So mass of metal, C of metal, change in temperature, the initial temperature of the metal 200 minus temperature at thermal equilibrium 22.4 must be equal to mass of water, C of water, okay, times temperature at thermal equilibrium 22.4 minus the initial temperature of water, which is 20 degrees Celsius. So we are told that the mass of the metal is 0.05. C of metal, we don't know. What is 200 minus 22.4?
177.6.
Come again.
177.6.
Okay. So 177.6 is equal to the mass of water is 0.4. Specific heat capacity of water 4200 minus times, this is 2.4. So Cx would be equal to, multiply this one for me. Multiply that for me.
It's a hot
32.
4032.
Yes, please.
Okay, so this is 4032 divided by, give me this product.
8.88.
Come again.
8.88.
8.88. So
Plus
that
P.
when we divide 4032 by, we have 454, approximately 454 joule per kilogram per Kelvin or degree Celsius. So that's the specific heat capacity of the metal. What about the second question? What about the second question? Calculate what is the energy transferred to the water as the metal is cooled. Yes, who was able to? Who was able to do that? Eva, were you able to do it? Julian, were you able to do that?
Sir, no.
Oh, what is the energy transferred to the water as the metal is cooled?
Sir,
Right.
is it a straightforward answer or is calculation?
It's calculation.
Ah.
What is the energy transferred to the water? You see, the principle of conservation of energy, heat lost by the metal must be equal to the heat gained by the water. So what is the heat gained by the water? And heat gained by the water is the energy transferred to the water after the metal is cooled. So heat gain, fuel gain by water must be equal to whatever we have here. Must be equal to 0.4 by 4200 by 2.4. And calculate this for me. And this is 4. That's the heat gained by the water. And if we substitute the value of this Cx into it, this must also give us almost the same value. So heat loss by the metal is equal to heat gain by the water. So this is the energy transferred to the water as the metal is cooled. Okay, so just read the question, and it's not a difficult one. Please, any question? Any question? Okay, tomorrow
No, please.
we'll be looking at change of states. Change of states, and I'm sure we'll also look at expansion in solids. Change of states. Change of states. So with change of states, we are looking at the energy that must be absorbed by a substance in order to change state from one form to another. Okay, the basic change of state we usually talk about, we have change from solid to liquid. And what is the name given to the change of state from solid to liquid? What name do we give to this change?
Melting.
Melting. So melting or fusion. We also use the term fusion to describe change of state from solid to liquid. Then we also talk about change of state from liquid to solid. What name do we give to the reverse of this? From liquid to solid. Hey, What's the name given to this change of state?
Freezing.
Freezing or
Solidification.
good? Solidification. Then change of state from liquid to gaseous. This is, what name do we give?
Vaporization.
Vaporization. Vaporization or
Evaporation.
evaporation. And then from gaseous state to liquid.
Condensation.
Condensation. Then solid to gaseous.
Sublimation.
Pardon, Michelle?
It's sublime.
So sublimation. These are a few of the process of change of state. Now, for a solid to change to liquid, what must happen to the liquid, the solid, in order to do that? What must happen to the liquid, solid, in order to change state from solid to liquid? Elizabeth?
It must be heated.
So the solid must absorb heat energy from outside. It must be heated, meaning there must be an external source of heat or energy given to the solid or substance to absorb. So fusion or melting involves absorption of energy. Then freezing. Freezing requires emission of energy, meaning this time around the heat is within the substance, which is the liquid, and the heat which is within the substance must be given out, thrown away, liberated, emitted, for the substance to, for the molecules of the substance to come together again. So that is why if you put something in a freezer, all that you are doing is that you want the freezer to extract the heat within the substance. Okay. And it is of the same reason that when you pass, okay, or feel the air at the back of the freezer or the fridge, it feels very warm because it is the heat energy that is extracted and is being blown out by the fan. So that is the reason. So freezing or solidification involves emission of heat energy from the substance, whereas melting requires absorption of heat energy. Then the next one is vaporization. What do you think must happen to the liquid before it turns to gaseous? Will it emit or absorb energy?
To absorb energy.
It must absorb energy. The energy absorbed breaks the bonds between the liquid molecules. And when the bonds are broken, the molecules are liberated, are free to move about, thereby changing to gaseous. Then the last, this one, gaseous state, turning back to liquid. Condensation, must it absorb or emit heat, external heat? Will it liberate or absorb? Oh, will it emit or absorb heat energy for condensation?
Absorb.
Hey, yo, condensation,
Oh, wait, emit.
it has to
So emit.
emit or give it out. And what do you make of sublimation? Revoir.
Mr. Area, please, I have a question about the condensation one.
Go ahead.
Won't the doesn't it have to absorb a bit of heat before?
Revoir. If you heat water and then
Yes.
you remove the lid and then cover it with a mirror, what happens? The vapor
The
on,
water will cool.
the
The
vapor
vapor will.
on striking the mirror will turn back to water. Meaning the temperature
Yes.
the temperature of the mirror must be less than the temperature of the vapor. And when that happens, okay, the vapor will turn back to liquid. So condensation, which is a process by which gaseous substances changes to liquid, involves emission of heat energy. The vapor must give out the energy absorbed, which took it to vapor. Are you okay? Are you okay?
Yes, please.
All right. So that's it. So solidification, sublimation is also involves absorption of heat energy. So we'll go into change of state. Okay. Julian.
The sublimation. Camphor, for instance, when it's just there, like you put in the bathroom and it's just there, there's no heat that's applied to it. That will make it like blind.
Yo, let me also ask you a question. Julian, if you have an ice block, and then you just put it on a table, what happens?
It melts.
It melts. When it is melting, it means it is absorbing heat energy to change from solid to liquid. Do you see external heat energy supplied to it? Do you
like external, like apart from the heat absorbing?
No, what I'm saying is that once you put it on the table and it's melting, do you visibly see external heat energy given to the ice block?
No.
It is picking that from the surrounding. Okay. It is picking that from the surrounding. You see, do you know methylated spirits?
Yes, sir.
Good. When you pour methylated spirit on your hand, within a short length of time, you feel coolness. At that, it will evaporate and you feel that coolness at that spot. Meanwhile, when you pour water on your hand, you wouldn't feel how pouring methylated spirits or spraying it there would feel. Okay. All these processes absorb energy from your skin. So in the case of the spirit, it is energy absorbed from your skin, which changes it to vapor, the reason for which it quickly dries. But water, because water has a very high heat capacity, the heat energy absorbed from your skin is not enough to change it to vapor. The reason why when you pour water, you wouldn't feel that coolness as methylated spirit. All that I'm saying is that the heat energy is absorbed from the environment and then from the spot of contact or from contact. Are you okay?
Yes, sir.
All right. So we'll go into this tomorrow once we have another session tomorrow. If you don't have any question, then this is where we draw the curtains on our meeting today. Thanks for your attention. Thanks for your question and everything. We'll meet possibly Not the same time though, but once again tomorrow. May the good Lord be with you. Take care of you. And in fact, bye-bye.
May the Lord be with you also.
Yeah, thank you.
Bye bye.
Bye-bye.